All right, we're going to go through 10.2 today. So our learning goals for 10.2, we have two of them. The first one is identify congruent arcs and find arc measures. The second one is I can prove circles are similar. That second one we've actually kind of already talked about. I think we already talked about ways we can prove circles are similar, but we'll review that. Make sure we all remember what we talked about back in chapter 8. Okay, we got some more definitions. I would pause this for a second and write these down. But here, let me run through them really quick. A central angle is an angle whose vertex is at the center of the circle. So an example of that would be angle ACB. So if I look at that angle, the vertex of the angle is right there in the center of the circle. So we call it, right, central angle. An arc, I don't have the definition of an arc up there, but an arc is just part of a circle. We're going to talk about three different types of arcs. The first one is a minor arc. A minor arc is an arc formed by a central angle that is less than 180 degrees. So this arc right here, AB, we refer to as a minor arc. And the reason why is because the central angle right here is less than 180 degrees. The way you write that, if you want to see arc AB, is simply just put AB, and you put a little arc over the top. That's the notation that we use. And again, it's a minor arc because that central angle is less than 180. If your central angle is greater than 180, an example, so if I go this way, I take this angle, I go this way, that's bigger than 180 degrees. That means this arc that goes with it out here, we say instead of being a minor arc, we say that it's a major arc. The way we write that, if it's a major arc, you always include a third letter. So I would call that arc A, ADB. And so A, that crosses through D, and it ends at B. We put a little arc sign at the top. So for major arcs, you always include 3 letters. For minor arcs, you only include 2 letters. The last one's a semicircle. I think we all know what a semicircle is, right? Half a circle. So if you have that, like it says on here, that the measure of the central angle is 180 degrees. So if I draw a diameter across there, if the arc's 180 degrees, let's name this something. Let's call it E. That means that this arc, BAE, we would say is a semicircle. So arc BAB, and it doesn't matter if you say EAB or BEA. Oops, that one doesn't matter. That was wrong. Sorry. You could say EAB or BAB. Just make sure that your endpoints B and E have to be at the start and the end, and then you have this one letter in between. So that's what a minor, major arc are, semicircle. That's how you name the arc, the notation. And just don't forget what a central angle is. It's going to be important for us. You'll see that right now here in just a second. Okay, so this is talking about the measure of an arc. So this is the measure of a minor arc is the measure of its central angle. So what it's saying is this central angle is 50 degrees. That means we say that arc is 50 degrees. And you see that notation there. We would say the measure of arc AB is equal to whatever that angle is. So the arc has this arc has the same measure as the central angle. If I wanted to find this major arc, so let's say we want to find the measure of arc ADB. That's this arc right here. It's 360 degrees all the way around. So all I would do is go 360 degrees minus the 50. Right, subtracting out that piece right there. So the answer to that one comes out to be 310 degrees would be the measure of arc ADB. So if you're trying to find the measure of an arc, think of the measure of the central angle that intersects the arc, that forms the arc, and that's going to be the measure of your arc. Okay, so this really quick. So this says RS, find the measure of RS when I come up here. This one's really simple. If that's RS, look at the central angle, it's 110. The measure of RS is 110 degrees. RTS, so let's outline that, make sure you know what arc we're talking about. So RTS looks like this. Well, that would be, right, that angle right there, it's 360 minus 110. That's going to be what, 250 degrees? Should be to measure that arc right there. Arc RST. This one's a little bit trickier. RST is like this. If you look up here, though, it does tell me that RT is the diameter. That means that is 180 degrees. It's halfway around the circle. So we'd say that RST is a semicircle. The measure is 180 degrees. This, I don't know that you need to write this down. I guess you can if you want. This seems pretty obvious to me. But all it says is if I want to find the measure of arc ABC, that whole arc, I can take the measure of arc AB plus the measure of arc BC, add it together, and it gives me the measure of the entire arc. Again, that seems rather obvious. I don't know if you need to take the time to write that down. Let's do a couple more problems. So arc GE. So GE, it's just those two angles. Those are the two essential angles that form those two arcs. So if we add those together, it'd be 120 degrees. GEF. So GEF is going all the way around there. I'm just going to add those three central angles together to get that. So 40 plus 80 plus 110, so it's at 230 degrees. GF. So be careful. Sometimes we get confused when we think of this as our GF, right? It goes from G to F. But if there's only two letters, it's talking about the minor arc. So GF is actually going to go this direction. Probably the easiest way to find that one is just to go 360 minus and take off that RGEF we just did. So minus 230. I subtract all those off. That's what, 130 degrees. Here's the answer right there. We're going to skip past that one. You guys try this one. So I'll pause this for just a minute, work through those 6 examples, get your answer, and then I'll run through really quick and give you the answer so you can check it and make sure you got it right. TQ, if this is my central angle, right, TQ is just 120 degrees. QRT, so QRT is this all the way around to there. Probably the easiest way to do that one is just go 360 minus this arc right here, so minus 120. So that'd be 240. QRT, measure of QRT is 240. TQR, TQR, that's 180 degrees. QS, that would be this one right here. So QS, I could go 360 minus those two angles. That's 200. So you have to get 160 degrees. And the last one, RST. Let's see, RST. That looks like a straight line. So that looks like a 180 degree angle right there. But if you're not sure, right, those two have to be 180. So you go 360 minus 180, you get 180 for RST, for the measure of RST. Okay. So make sure that makes sense to you. Here's our next theorem. This one says two circles are congruent if and only if they have the same radius. So hopefully that kind of makes sense, right? If I were to take this circle, if I were to take that circle and enlarge it, so let's enlarge that. The radius gets bigger, right? So the only way two circles can be congruent, right? Congruent, they're the same, is if they have exactly the same radius. By the way, the if and only if part means it goes both ways. So that means if the circles are congruent, then the radii have to be congruent, or if the radii are congruent, then the circles have to be congruent. So it goes both ways with that if and only if. Here's your next one. It says congruent central angle theorem. So it says in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding central angles are congruent. So what it's saying is, if I have this circle up here, these arcs, arc DE and CV, they can only be congruent if those central angles are congruent. So if those two are the same, that means those arcs are congruent. They have the same length. It also says, it's also true, right? It says if you have congruent circles, so if I take a circle, I'm gonna draw me a quick circle down here. It wasn't the greatest circle, use your imagination. But if I have two congruent circles that are exactly the same, then the same thing is also true. So say I measure an arc over here, and I measure that angle, and I measure an arc over here, and I measure that angle. As long as those angles, that angle and that angle are congruent, and the circles are congruent, that means the arcs will also be congruent. So you can compare arcs within the same circle, or you can compare arcs on two congruent circles. And as long as their central angles are congruent, then the arcs will be congruent. So here's three examples. It says, tell whether the red arcs are congruent. And it's kind of hard to see the red on here, but this first one, like here's an arc, and there's an arc. We want to find out, are those two congruent to each other? There's two basic things you check off. Number one is this theorem only applies if the arcs are in the same circle or congruent circles. And the second thing is the arcs are only congruent if their central angles are congruent. So central angles are congruent. So if you look at this problem, well, we got the same circle. So number one checks off. They're inside the same circle. The second thing is, are the central angles congruent? Well, that one's 80 and that one's 80, so that one also checks off. So the question is, are those two arcs congruent? And the answer is yes, they are. It meets the two requirements. Okay, B, if you look at that one, this is my one red arc, that's my other one. Are those two congruent to each other? Well, the first requirement is they have to either be the same circle, they're not the same circle, or they have to be congruent circles. These are not congruent circles, right? The smaller circle, you got a smaller circle and a bigger one, they're not congruent. So it doesn't meet the first requirement, so the answer is no. And my reason would be is the two circles are not congruent. By the way, just to differentiate, if I find the measure of this arc, RS, it's 90 degrees, and the measure of arc TU is also 90 degrees. So they have the same measure, the same degrees, but they're not congruent. Like if I were to measure this one is shorter than that. Okay, look at C. So again, our two requirements, are they the same circle? No. Are they congruent circles? Well, if you look at this, it shows that radius is equal to that radius. That was that previous theorem we just went through. It says if the radii are the same, then they're congruent. So number one's checked off. Okay, we know that they're congruent. Check off number one. Number two is, do they have the same central angles? Well, that one's 95, and that one's 95, so number two is also checked off. So this one would be yes, and why is because the two circles are congruent and their central angles are also congruent. You guys pause it for just a second, take a look at these two. You decide if the red arcs are congruent or not. By the way, the red arcs are AB and arc CD, and it's arc MN and PQ. So you guys check that really quick. Okay, I'm going to give you the answers here. Can we show that the two circles are congruent? The answer is yes. Number one thing, let me start over there. So the number one thing, are the circles congruent? Yes, we can check that off. The number two thing is, are the central angles congruent? Well, they're both 145, so that also checks off. So the answer number 7 would be yes. Number 8, so check off number 1. Are they either the same circle or congruent circles? They're not the same circle, and they're not congruent either because they have their radius of each circle is different. So you can't check off number 1, so we stop right there. The answer is no. Those two arcs are not congruent to each other. Okay, this is the last theorem. This is saying, it's really simple. It says all circles are similar. I think we can think about how we can prove that. If you remember back in chapter 8, we said to prove two shapes are similar, or two figures are similar, we can show through a series of rigid transformations and a dilation. So if you look at that, this one's pretty easy, right? Circles are all pretty easy. I can do a translation to match that up, and then you can just do a dilation. Mine's gonna be off by, I gotta readjust it. Then I can do a dilation to show that the two match up. And that will work with any two circles. You can always match them up. So that means, just like this theorem says, that all circles are similar to each other. Okay, that's it for 10.2. Thanks.